Hello, hello. Test, test. Hello, hello. Is it working? Can you guys hear now? Joseph and Dylan? Okay, sorry about that. Okay, so let me just repeat what I said quickly then. We have a unital C-star algebra, and we had two special types of elements. One is the self-adjoint element when it's equal to its adjoint, and another is a unitary, which means that it commutes with its adjoint, so it's normal, and its adjoint is actually its inverse. And then at the end, we observed that the spectrum of a unitary element is always contained in the unit circle. Okay, so this will actually allow us to say something about the spectrum of self-adjoint elements. So 2.1.11. First, we need the following. So take a unital C-star algebra. And an element A, not necessarily self-adjoint or anything special like that. Then we can define an element e to the A as the infinite sum of a to the n over n factorial, and for every a, b in A that commute, we have that EA plus B is the same as EA times EB. Okay, so proof. Well, the first observation is that this is indeed a well-defined element in our C-star algebra, and that's because we have that submultiplicativity of the norm. This will converge in R, so indeed this EA will be in A. Since our C-star algebra is assumed to be complete, we always have this limit will also be in our C-star algebra. Okay, so next, the idea is to show that, or maybe check that if that the map phi A from R into the C-star algebra A, given by mapping T to E to the TA, is differentiable. So this should remind you of what characterizes the exponential function in regular analysis. So this is at every T in R. And its derivative is given by what you expect it to be. So we just take out the A there. Oops, be a 5. Sorry about that. And it satisfies the condition that phi A of 0 is going to be equal to the unit of our C-star algebra. Okay, so that's an easy thing to check. And then moreover, if we have some other function that satisfies exactly these properties, then it has to be this phi A. Okay. So now note that if A and B commute, then we can make sense of this for A and B. And we can check that the function will satisfy the correct properties. So we want that derivative will be A plus B e to, well, by t. And at 0, it will be 1. So we can conclude that indeed this is well, just the exponential function applied to A plus B, I guess. That's this. So in particular, we get the desired result. Okay, so note that, of course, A will always commute with minus A. So if we plug in A and minus A here, we just get 1. So in particular, e to the A was always invertible. So okay. Yeah, you probably just need a Banach algebra. Yeah, this does not require the star. That is true. So yeah, so this could just be unital Banach algebra. It just needs to be unital and complete. Yeah, you're right. With a submultiplicative norm. Okay. Another proposition. And this is about the spectrum now of a self-adjoint element. So if A is self-adjoint, so remember this is our notation for the set of self-adjoint elements, then the spectrum is real. Okay, so by our previous proposition, well, actually, this is really by the previous observation, I suppose. E the IA is invertible. And since A itself is self-adjoint, what does this inverse look like? We have E minus IA is the inverse, and that's the same as EIA star, which is, of course, okay. So what does this mean? Well, the inverse of this element is given by the star of the element. So that means this guy is a unitary. And so we know its spectrum is going to be in the circle. So now take an element lambda in the spectrum of A. And set B to be the following element. So we're going to sum from n equals 2 to infinity, I to the n, A minus lambda, n minus 1 over n factorial. Then this is just some infinite sum with A's and lambdas. So this should be lambda times 1 to be a little bit more specific. So it commutes with A. And moreover, we have that EIA minus EI lambda is the same as EIA minus lambda minus 1A, which is, oops, sorry, times EI lambda. So just taking out the EI lambda. And then you can check that this is indeed going to give us A minus lambda B EI lambda. Subbing in this thing here. And lambda is in the spectrum of A. So that means that this is not invertible. Hence, this EI lambda is actually an element of the spectrum of EIA, which means that it has to have absolute value 1, which implies that lambda has to be real. Okay, so that's another nice thing we can say for a C-star algebra. And just another quick observation. Yeah. If we have an element A and A, then of course A star A is going to be self-adjoint, so that's easy enough to check. So the span of A star A is always in R. And we have the C star identity telling us that the norm of A is just the norm of A star A half. Okay, which is so this is going to be the supremum of those lambdas. Well, they're going to be in here, but the spectrum of this is going to be the same as so we get that this is the supremum A of the absolute value of lambda. Okay. So then this is quite nice because this actually is telling us that the norm of A actually only depends on the spectrum of A. So that gives us the following theorem, which is really quite a nice theorem. If we have a star algebra, and it has a norm which makes it into a C-star algebra, then this is the unique C-star norm making A into a C-star algebra. So here's another place where you see that C-star algebras are somehow much better behaved than just arbitrary Banach algebras or even Banach star algebras. You get something like a norm, which is very much a analytic sort of thing, and it's actually just completely determined by this algebraic type object. Okay, we'll need to erase some boards. Okay, so again, a lot of the things we've shown so far have been for unital C-star algebras. And we would like to be able to talk about non-unital C-star algebras. So to do this, we need a notion of a unitization, which is our next section. So as I mentioned, I'm more or less following the book, An Introduction to C-star Algebras in the Classification Program. And there, this section contains also information about the multiplier algebra, but I'm going to leave that out for now because I don't think we'll need it in the near future, and maybe we can sweep it under the carpet. But of course, please read it if you like. And anyway, so the point is that this section will be a bit short. It probably doesn't really deserve its own section title, but just to keep the numbering easier to follow, I will still do that. Okay, so recall that if we have a non-unital Banach algebra, well, it doesn't have to be non-unital actually, but we can always attach a unit. We had this A tilde, which was A plus the complex numbers, and we had just coordinate-wise addition, and the multiplication was given by this funny thing. And we had the norm on A to be, sorry, on A tilde to be the norm of A as an element in A plus the absolute value of lambda. And this was a, if we think about A, since it's, we can obviously just map A to A tilde by sending A to A comma 0, then this was an ideal. A is an ideal in A tilde. Okay, well, we can obviously do this as well with a C-star algebra. Doing the exact same thing because the C-star algebra is a Banach algebra. But the problem is that this will not actually be a C-star norm. So maybe I should call this something else. I'll call it Banach algebra norm. Okay. This is not a C-star norm. So we have to be a little bit more clever to define a norm. So, okay, first of all, it's clear that we can just define the star operation in the obvious way. So, well, okay. But we will need to equip it with instead the operator norm. So we've already seen this in several guises, I suppose, but let me just recall here what I mean exactly. So if we have a linear operator between two C-star algebras, this is just defined to be primum of the operator T applied to A and B, whoops, where A has a norm at most 1. Right. So this is really just the usual notion of an operator norm between A and B, where we're thinking of them now as just Banach spaces and forgetting that they're C-star algebras. And this allows us to define a norm. There's something weird with the tabs. I don't know what's going on. This allows us to define the norm we want on our unitization. take a C-star algebra now. We call minimal unitization. I'll usually just say unitization, and I'll mean this particular unitization, but it is minimal in a certain sense that we probably won't really talk about. So it's defined by, again, I will denote this by A tilde. As a vector space, it's just the direct sum of A and C. Coordinate wise addition. The same multiplication as we had for the Banach unitization. And the star, as I said, is just what you would expect. So you just take the star of the first guy, and the star in the complex numbers is just complex conjugation. And then for the norm, we take the operator norm where we consider an element of A tilde as a linear operator on A. So for every A lambda, we can think of this as an operator on an element in our C-star algebra A. So it's easy to see that this is a linear operator from A to A. So in other words, the norm of A lambda is going to be the supremum of AB plus lambda B. The norm is now taken in A, and we want B in A with norm at most 1. So this actually does make A tilde into a C-star algebra. And just as before, we can identify A as a C-star subalgebra in A tilde, and it will actually, moreover, be an ideal. Okay. So this ideal is as you can see, quite large. It's most of A tilde. And this A tilde is now a unital C-star algebra, which is why we call it a unitization. And this is somehow the smallest unital C-star algebra that you could put A into, which is why we think of it as minimal. And there are other useful unitizations one considers, such as the multiplier algebra, which tends to be quite a lot more gigantic and a bit unwieldy at times. So depending on what sort of properties you're looking for, will allow you to choose which unitization is useful. But for our purposes, we will almost always only need this minimal unitization. And as an example, if we have continuous functions on a locally compact algebra space, recall last time that we saw that that was a nice C-star algebra, then what do we get? X is locally compact and Hausdorff. These are the continuous functions vanishing at infinity. Then its minimal unitization is just the continuous functions on X, where we attach a new point at infinity. This is the 1-point compactification of X. So in this case, you can see that there could be other unitizations by taking different compactifications of X. But we were interested in this one for now. Why is this useful? Because again, just like we could for Banach algebras, we can often reduce proofs about general C-star algebras to ones that are unital. So, okay, so the question for those in cyberspace, the question was, if A is already unital, should we assume that A is equal to A tilde? And well, the answer is you can attach a unit to a unital C-star algebra. That's fine. This is a different C-star algebra, but usually if it's unital, I won't bother doing this because I don't need to. So hopefully I will specifically mention when I am doing that so that it doesn't cause confusion. Okay. So for example, here's a not very difficult thing, but also very useful. If we have star homomorphism between two C-star algebras, so recall this is just an algebra homomorphism that also sends adjoints to adjoints. then there is a unique extension to A tilde, which is going to be a unital star homomorphism. So we don't know that B has a unit, so okay, this is actually exactly where this problem that was just pointed out could occur. So if B is already unital, then it has a unique extension that sends the unit of A tilde to B. If B happens not to be, well, okay, then we have to extend it to B tilde. So here we get another nice result about C star algebras, which essentially gives us analytic type information from purely algebraic information. So we have a star homomorphism. Phi from A to B. Then it's automatically norm decreasing. So phi of A, an element of B is always less than the norm of A in A. So in particular, every star homomorphism is continuous. So to prove this, we will use our trick of passing to unitizations if necessary, so that we can assume everything is nice and tidy and unital, which will make things quite a lot easier. And then this will essentially follow from what we observed about the uniqueness of the C star norm being determined by the spectrum of an element. So if A and B are not unital, or if Y itself is not unital, well, we can just replace them with their unitization. And if they are unital, we'll just leave them as they are. We can assume that A, B, and phi are all unital. So recall that a unital star homomorphism just maps the unit of A to the unit of B. Okay, in that case, it's easy to see that this will be invertible in B if A is invertible as an element of A, and in turn, this implies that the spectrum of an element phi of A after applying phi is going to be subset of the spectrum of A yes. Yeah. Sorry. Sorry about that. Right. So this implies that this element is bounded by the spectral radius of this guy, which is of course the norm of A, and that gives us the result. And as a corollary, any star isomorphism is automatically isometric. Which again is something you wouldn't necessarily get if you were not in the context of a C-star algebra. Shop is getting rather small. Okay, so now we'll talk about the Gelfand-Naimark theorem. So we saw the Gelfand transform for Banach algebras in the last lecture, I believe. And for C-star algebras, we get slight improvement on that result. And this is really one of the most fundamental theorems in C-star algebras. Okay, so just to recall that we had the character space of A is a commutative. Yes, we also wanted it unital. No, we don't need it to be unital. Commutative. The character space was denoted by omega A. And characters were just algebra homomorphisms from the algebra into complex numbers. Okay, Well, we have a special type of character. In the case of continuous functions on a compact Hausdorff space, and take an element x and x. I wrote this as a definition, but it's really sort of sneaking in a little proposition at the same time, but okay. I hope you'll allow me that. So define the evaluation map of x. This goes from C naught of x into C. What does it do? It just takes f, a function, and evaluates it at this point. This is a character. So I didn't tell you what A was. All right, I have to use a new chalkboard. That's why. So this is a character for C0 of x, and that's easy thing to check. In fact, we had something a little bit nicer. So recall, I guess I should have recalled this before, but we put the weak star topology on the character space. So now we're considering actually something compact. Then we can define a map omega from x to the character space, which takes x to the evaluation map at x. And this is a homomorphism. Okay. first, let's show that this map is actually continuous. So we'll take a net. If you're not so familiar with nets, then replace Hausdorff with metrizable, and then you can take this just to be a sequence. And we want the limit of this to be x. Then we have that evaluation of x lambda of f is f of x lambda. And if this is a net converging to x, since f itself is continuous, this will converge to f of x, which is of course just the evaluation of f at x, and this is true for every f. So this converges pointwise to this, which is exactly what we want in the weak star topology. So we get continuity. Okay, now we want to show that it's injective. Okay, so suppose we have 2 points in x that are not equal. Then we can use Urysohn's lemma. We know that there exists some function that is 0 on x, but 1 on y. Okay, now if we have take a character in our character space of T of x, and note that the function f minus tau of f times 1. This is obviously going to be in the kernel of tau. And we also have that f minus tau f. This function evaluated at x is different from this evaluated at y. by the Weierstrass theorem, there exists some z in X such that g of z is 0 for every g in this kernel. So g is in the kernel of tau. Evaluating this function at z gives us this. This is then just equal to tau of g. Since g of z is 0, and this is 0 because tau is in g is in the kernel. So that tells us that tau of g is g of z, and thus that our character is evaluation at z. So wait a second. I have accidentally skipped something and making no sense. Something. Oh, sorry about that. I should have said here that and this was the injectivity, and then, sorry, this was the start of the projectivity. Sorry about that. Anyway, so this shows that surjective. Okay, so we've shown that we have a continuous bijection from a compact space, which is automatically a homomorphism. Okay, so we're just about to come to the Gelfand-Naimark theorem. Oh. We're having some minor technical issues again. Sorry about that. That are hopefully being solved in less than 6 seconds. 5, 4, 3. Yeah. So I'm assuming that even though everyone just disappeared from my point of view, you can still hear me. All right, so as I said, we're about to prove the Gelfand-Naimark theorem. Let me just clean some chalkboards. First, a useful remark. we have a C-star algebra, and we have an element A. Actually, suppose if it's true for just a star algebra. Then if we write oh no, I made a mistake, haven't I? I'm not self-defined. I always get this wrong. I don't know why. But okay. Then we can always find two elements, B and C, that are self-adjoint, such that A is equal to B plus IC. And I was about to try to write down what they were, but it seems I have a minus sign problem, which is too early for me to fix. But then where do you divide by 2i? And then, oh, I guess the other one is A plus A star over 2. Okay, so this is B. Aha. Thank you, Tristan. It's hard to think in public sometimes. Okay, so that brings us to the Gelfand-Naimark theorem. So we have a commutative C-star algebra. Recall that in particular, it's a Banach algebra, so we can consider the Gelfand transform. And in this case, it will actually be a star isomorphism. So recall that this was the map that sends A to A hat. This is a star isomorphism. Okay. Take some character and self-adjoint element. We know that the characters by applied to A are always in the spectrum of A, and this is self-adjoint. And we saw that that is real. And then using the trick in the remark, if we write B equals A plus IB, where A and B are self-adjoint, we have that phi of C star is phi of A minus IB and that is, of course, same as phi of C conjugate, which means that this is a right. So this implies then that E hat star applied to phi is the same as E hat phi. And that's for all C in A and phi in omega A, which tells us that this is indeed a star homomorphism. So we would like to show that it is bijective. And for that, it is enough to show that it is isometric and surjective. So since it's isometric, that will imply that it has to be injective. And then surjectivity will give us that it's actually a star isomorphism. So what we also, knowing that phi A is in the spectrum, this also tells us that, and that this is a star homomorphism, we can find out what the norm of this guy is. And well, using the C star identity, that's A hat star, A hat, which is the same as A star A hat. And this is just the spectral radius of A star A by definition of the hat, which is of course just the norm of A star A, which is the norm of A squared. So gamma is isometric. And now that it's surjective, follows from Stone-Weierstrass theorem. By observing that it will separate points So it contains separates points and contains functions that don't simultaneously vanish on some non-empty subset. So that tells us that indeed gamma A is all of C naught of A, omega A, which is what we want. Okay, so now we know exactly what a commutative C-star algebra is. It's always the algebra of functions on some locally compact Hausdorff space. And indeed, if it's unital, then we can take X to be compact. So that's all well and good, but it's a bit annoying because, of course, in practice, you're not going to be surrounded by commutative C-star algebras all the time. However, this theorem actually has some very nice repercussions for not necessarily commutative C-star algebras. And that is that it gives us this continuous functional calculus, which is really one of the most useful tools in C-star algebras. Okay, so just a bit of notation. If A is a C-star algebra, and we have some subset then I will denote the C-star algebra generated by S is denoted by C-star of S. So this is the smallest C-star algebra containing S, or equivalently, take all the C-star subalgebras containing S and take their intersection. That will give you C-star S. So take a unital C-star algebra and let A be a normal element. So that means that it commutes with its adjoint. Then the map gamma from the continuous functions on the spectrum of A into A, which maps the function identity to the element A. This is an isometric star homomorphism whose image is the C-star algebra generated by A and the unit of the C-star algebra. this is isometric star homomorphism. Whose image is the C-star algebra generated by A and the unit of 1A. Okay, A is normal. So that means that the C-star algebra generated by A and the unit is actually a commutative C-star algebra. So by our previous theorem, we get that the Gelfand transform applied to this C-star subalgebra is a star isomorphism. Now we saw last time that the map H from the character space of this C-star algebra to the spectrum of A is a homomorphism. So that allows us to define a map from the continuous functions on the spectrum to the continuous functions on this character space by composing with H. So we have a star isomorphism continuous functions on the spectrum to continuous functions on this character space by mapping a function to F composed with H. And if we take specifically F to be the identity, so and let gamma be gamma inverse composed with psi, then we see that gamma of F gets mapped to A. And indeed, this is the unique unital star homomorphism with this property. So indeed, it is the map we just saw. And it's easy, since we're composing two star isomorphisms and then just restricting it to something. we get that it's isometric. And since it's generated by this function, f of z equals z, and the unit, and this gets mapped to A and to the unit, we get that its image is just what we wanted it to be, which is this C-star algebra. Okay. So I have 5 minutes. So I will just say some of the things rather than writing them down. Okay, obviously I said this just for unital C-star algebras, but you can make an analogous statement for non-unital. Then you need to take spectrum of A will only be locally compact, so you need the functions vanishing at infinity, and now your image will not be the C-star algebra generated by A and 1A, but just by A, since there is no unit. And this Gelfand theorem gives us actually a categorical equivalence between compact Hausdorff spaces with continuous maps and unital commutative C-star algebras and star isomorphisms. Okay, so let me just give this last. Theorem, which will show you how we get to use this nice result. So let A be a C-star algebra and A a normal element. And for any function in continuous functions on the spectrum of A, or possibly those vanishing at infinity, the element f of A is normal and satisfies spectrum of f of A. So I'll need to tell you what this is in a second. Is just f applied to the spectrum of A, and if we have some G that's defined on the spectrum now of f of A, then G of f of A is the same as G of f of A. Okay, so I need to justify this notation. Recall that we had this polynomial mapping theorem in maybe even the first lecture, which said that if you have an element, it makes sense to consider the polynomial with A plugged in that to the indeterminate. Now, if A is normal, it commutes with its adjoint, so we can actually consider polynomials in two commuting indeterminates now, and that makes P of A make sense whenever A is normal, and it's clearly an element in A. But of course, polynomials are dense in C of SPA, which means that you can take F approximated by polynomials. Of course, our C-star algebra is closed, so this gives you a well-defined element F of A. And the fact that it's normal, again, you can see that by approximating F of A by polynomials. Any polynomial of a normal element is going to, again, be normal. And similarly, one can check this in the analogous way. Okay, so I will stop there for today. I managed to only go over by a little bit less than a minute. And so we'll see everybody next week.